Hey again to all my juniors that are still following along with distance learning. Glad to still have you here. We're talking about this really cool concept, one of my favorites, called matrices. In this lesson we're going to talk about determinants of matrices and also what an inverse of a matrix is going to be. So first thing, talk about the determinant of a matrix. We'll only have it for square matrices. So every square matrix will have a determinant. It's going to provide us information about a matrix that it's useful in a couple cases, particularly solving systems and with calculating the inverse of a matrix. So these are topics we're going to explore in this lesson and the next lesson. First thing, determinant of a matrix, it's denoted with bar symbols. It's important that we understand that this is not absolute value. Yes, it's the same symbol, but when we're talking about matrices, that does not mean the absolute value of A, that's meaning the determinant of A. Or in some cases you'll see it just written as DET, short for determinant of A. Almost like a function, even though it's not exactly a function. So first thing, there's a pattern, and I want to see if we can discover that pattern on our own. That's used to calculate the determinant of a 2x2 matrix. So I encourage you to look at each of these. I made one small typo. This should actually be an 8. It's corrected on your paper, but mine it's messed up on. See if you can recognize the pattern for how we get this scalar answer out of a determinant. Notice it is just a single answer, single number. It's a scalar value. So I encourage you to pause the video and see if you can recognize the pattern for calculating the determinant. Alright, coming back together, I realize a couple things. So, we're getting 3 here. What seems like it's happening, like if I multiply these two numbers, 4 and 2, 4 times 2, that's going to give me 8. And if I multiply these two numbers, 1 and 5, along that second diagonal, that gives me 5. Again, that was 1 times 5. That gave me 5. If we think about it, how do we get 3 from those two numbers? Well, we can subtract them. 8 minus 5 would give us 3. Well, let's see if that held up in the other ones. Maybe you saw this too. It seems like I'm multiplying 2 times 5, which will give me 10. Along the other diagonal here, multiplying 1 times 2 gives me 2. And if I subtract these values, it gives me the 8 that I wanted. Same idea for the next one. Negative 4 times 1. Numbers along this diagonal. Negative 2 times 5. These give us negative 4 and negative 10. Well, if I do subtract these, subtracting a negative is the same thing as addition, so this is negative 4 plus 10, and yes, this equals 6. So, seems like what we're doing is we're multiplying along these diagonals to get our answer. I actually saved a picture of this. Or no, I didn't. That's a later one. Seems like it's happening. We're taking for some 2x2 matrix, for a 2x2 matrix, the determinant is, well, it's a subtraction, so that's the difference. Difference is our word for subtraction. Between the product, because we're multiplying, product of, well, the first product we got was 4 and 2 in this case. This is the main diagonal going from top left to bottom right. This diagonal of any matrix is our main diagonal. So the product of the main diagonal and the product, because we're taking the product of the other diagonal, and this diagonal that goes from top right to bottom left, we call that the anti-diagonal. So for a 2 by 2 matrix, the determinant is the difference between the product of the main diagonal and the product of the anti-diagonal. Pretty simple to calculate, but let's just write a general formula for it. So if we have some matrix, in this case, A, B, C, and D, see if you can pause the video and actually write a general formula for the determinant of A. Alright, so hopefully you pause the video. What we're doing is we're calculating the determinant of A. You could use the symbol DETA if you wanted, but I use the bar symbols again. Well, it's the difference, so we know we'll be subtracting between the product of the main diagonal, which is A times D, and the anti-diagonal, which is B times C. So this here is our general formula. What's important though is this is only for 2 by 2 matrices. This formula obviously won't work for larger matrices, well, because we only have 4 values that we're using in this formula. So go ahead, use this formula, see if you can come up with a determinant of M. And then think about the determinant of N here. It's a larger matrix this time. Alright, when you found the determinant of M, you should have got negative 239. How you would have got that? 10 times negative 23 minus 1 times 9. You should have got negative 239. Alright, in the case where we have this larger matrix, things get a lot more difficult. What's not going to make sense is this diagonal idea anymore. If I were to just take 2 times 6 times 2 along the main diagonal and 9 times 6 times negative 1 along the anti-diagonal, I'm going to ignore all of these values. That's not going to be useful to ignore things when we're calculating this determinant. So that same idea doesn't work. And the pattern would be a lot more difficult to notice if we were just to sit here and examine 3 cases like we did in number 1. So just to illustrate, because I'm never going to actually make you calculate by hand the determinant of a 3 by 3 matrix, I'll just show you where it comes from and then prove to you that it's going to be a lot easier just to use a calculator. Alright, so when we're calculating the determinant of a 3 by 3 or larger matrix, what we have to do is take any row we want. You could look at the second row. You could look at the third row. Most of the time I look at the first row, unless there are a bunch of zeros in another row. That is a whole other case. But I'm going to look at the top row. If I look at this 2, what I need to do is now ignore anything that lines up with it horizontally or vertically. And what we're going to do is multiply 2 by the determinant of these remaining values. So it would be 2 times the determinant of 6, 1, 7, 2. Next, we're going to have to take the second term from that first row, negative 5. Ignore everything that lines up with it, in horizontally or vertically, and then we'll take the determinant of those remaining values. But what we're doing here is we're actually going to subtract in between. So minus -5 times the determinant of 3, -1, 1, 2. All right, and now we have one more term in that first row. That was 9. So I'll ignore these and these. And we'll multiply it by the determinant of this. This time, instead of subtracting, we're going to alternate signs. So now the next sign is addition. So for every single piece, we alternate signs. It's another stupid thing that we have to memorize, which is why we shouldn't even bother having to use pencil and paper to figure out determinants of large matrices like this. So it would be 9 times 3, 6, -1, 7. Oh, what a mess. Now I have to sit here and calculate the determinant of each of these matrices. So this will be 2 times, well, 6 times 2 minus 1 times 7 minus -5. Well, subtracting a negative, that's just going to be adding 5 times the determinant of this matrix will be 3 times 2 minus 1 times -1. And then plus 9 times the determinant of this last matrix that we formed is 3 times 7 minus 6 times -1. And now we just have a bunch of simple math to do. This will be 2 times 6 times 2 is 12, minus 1 times 7 is 5. 12 minus 5 is 7. Plus 5 times, well, this is 6. -1 times -1 is 1, so 7. 5 times 7. And lastly, 9 times 21 plus 6 is 27. This ends up being 10 plus 35 plus 243 after I multiply each of those pieces. I don't know how I got 7 here. I meant to get a 5 here because this is 12 minus 7 is 5. I don't know if I said that or if I said 7. What's wrong with me? Add those all up and you get 288. So the determinant of this matrix is, after all of that fun work, 288. Alright, my point is, we don't want to bother with that. There are actually a bunch of online calculators that can do this for you. The one I want us to look at right now, because it's very user-friendly, minus ads, is Mathway. So, it's easy to access. Just go online. And it gives you a whole system here. It asks how I can help you. Well, we just want to enter a problem. There's a few ways we can do it. For the determinant, I'm just going to type DET. It seems like it already knows what I'm talking about. Changed fonts there. Hey look, there's this button over here that says matrix. Well, we have a 2 by 2 matrix. You can either click on these or you could change the numbers if you really want, but we have a 2 by 2 matrix. Click insert. The matrix we were looking at, actually, well yeah, for M was 10. Oops, I don't know why I clicked square root. Why do I keep clicking comma? 10, 1, 9, and -23. Press send. It asks, how should I answer? It gives you a bunch of things, some stuff that you've never heard of. Well, we just want to find the determinant. Click find the determinant, and it tells us the answer is negative 239, just like we wanted. The second matrix that we had was a 3 by 3. So again, we can type determinant. Enter our matrix, it's 3 by 3. We add 2, negative 5, 9, 3, 6, and 1, negative 1, 7, and 2. And it computes it for us, 288. All that work that I showed you will end up being true. The determinant of that 3 by 3 was 288, but I didn't have to think about it, which is awesome. So point is, this way is really great, especially when we have things larger than a 3 by 3, or yeah, especially a 3 by 3. Imagine 4 by 4, 1, 2, 3, 4, 6, 5, 2, 1, negative 1, 4, 3, 2, negative 6, 8, 5, 3. Calculating the determinant of this, I have to take this term, ignore all of these, then I have to calculate the determinant of a 3 by 3 matrix and multiply this by that whole 3 by 3. What a mess. That would take a lifetime. I don't want to do that. Just put that in a calculator. Alright, next thing. We need to understand what the multiplicative inverse of a matrix is going to be. In order to understand that, we got to think of what an identity matrix is. It's going to be a square matrix that has ones along the main diagonal and zeros everywhere else. For example, when we're thinking of a 2 by 2 identity matrix, it's like this. Ones along the main diagonal, zeros everywhere else. Alright, so what I want you to do is pause the video and create your own matrix F that is 2 by 2 and compute the products Fi, so F times I, and I times F, and explain what you notice. So go ahead and pause the video and give that a shot now. Alright, for me, let's say that I let F be 1, negative 2, 3, and negative 4. So I just made this matrix up, wanted to put in some negative values for fun and see if it matters. So what we'll see is that when we multiply F times I, the identity matrix will have F is 1, negative 2, 3, negative 4. The identity matrix is 1, 0, 0, 1. Well, we've learned matrix multiplication now. We'll take terms along the first diagonal, 1 and negative 2, not first diagonal, first row, and multiply it by each of these and take the sum of those. It'll be 1 times 1. This will be our new matrix. And then plus negative 2 times 0. Alright, next we'll take the first row by the second column of the identity matrix there. So 1 times 0 plus negative 2 times 1. Alright, next we're going to take the second row of this first matrix, 3 times negative 4. Sorry, 3 times 1, we're multiplying it by here, 3 times 1, and then negative 4 times 0, sum of those. And then we'll go 3 times 0 plus negative 4 times 1. do this in another color. Alright, and now we can just add things up. Here we should see 1 times 1 plus negative 2 times 0. Well, that's just 1. 1 times 0 is 0, plus negative 2 times 1. Where did I get the negative 2? Oh, yeah, is negative 2. That's right. 3 times 1 times negative 4 times 0. It's 3. 3 times 0 is 0, plus negative 4 times 1 is negative 4. Hey, that looks pretty familiar. Hopefully you saw the same idea. Did this change? No, it's identical. After multiplying by the identity matrix, our answer stayed the same. Could do this again. Ask you to do it the other way around. I times F. Basically be 1, 0, 0, 1 times this matrix again. 1, negative 2, 3, negative 4. If you want to test it out, you can, but I'll just tell you, you get the same thing. 1, 2, 3, negative 4. So what do I notice? Well, regardless of order, the matrix F remained identical. So multiplying by the identity matrix did not change that matrix. So just like with real numbers, if you think back to real numbers, multiplying by 1 doesn't change a number. 1 is actually the identity for multiplication. In this case, it's not that different with matrices. Why is this called an identity matrix? Well, like multiplying a real number by 1, for example, 2 times 1 is still 2. Pi times 1 is still pi, etc. Think of any number, multiply it by 1, it remains identical. Multiplying by a square matrix by the identity matrix returns the original matrix. It stays identical. Alright. This idea also comes into play when we talk about inverses. We can use the identity matrix. Like, let's pause and think for real numbers. If I think of a real number, like let's look at 2 again, 2 times something will equal 1. Whatever returns the identity matrix here, that's going to be the inverse of 2. Well, what would we have to multiply 2 by to get 1? Well, 2 times 1/2. 1/2 is the inverse of 2. Think the same thing for numbers like pi. Pi times some number will equal 1. Well, what number? 1 over pi. Pi times 1 over pi is 1. These are the inverses. Same idea works here. For a matrix, the inverse of a square matrix A, we'll call A with the -1 exponent-like thing. It's not an exponent though, it just means inverse. Such that A times its inverse equals the identity matrix, or the other way around. That's going to be the inverse of our matrix. So we want to use what we know about matrix multiplication and system of equations to solve for the entries of the inverse matrix in the parts below. So basically they're saying 1, 3, -1, 5, this matrix times some other matrix will equal the identity matrix. But what is this matrix? We want to figure out what those entries are. So let's apply what we know about matrix multiplication. Multiply this out and we get first row times the first column, sum of those, 1w plus 3y. I know I don't need this one, so I'll get rid of it. 1x plus 3z. Again, I don't need the 1 coefficient. Now the next row times the first column, negative 1w. Again, I don't need that negative, or I don't need that 1. So negative w plus 5y. And then this second row times the second column, negative 1x, or just negative x, plus 5z will equal the identity matrix still, 1, 0, 0, 1. Alright, this is beautiful now because we can see a bunch of different equations. Notice these entries are in the same location. Therefore, we can set up an equation. W plus 3y should be equal to 1. Notice these are in the same place, so negative w plus 5y will be equal to 0. So we just set up a system of equations with the variables w and y. You can do the same exact thing for these two. A second system of equations, x plus 3z, was in the same place as 0. And negative x plus 5z will equal 1. And now we'll rewind to Algebra 1 and we'll actually solve this system of equations. I see this as useful because, hey, look, it equals 0. I could just solve for w pretty easily. If I add w to both sides, we'll see that w is equal to 5y. That was from this second equation. Well, now that I know what w is, I can plug it back into the first equation that we didn't use. We'll have 5y plus 3y equals 1. Gives us 8y by combining like terms equals 1. Multiply both sides by 1/8 or divide by 8 and you get 1/8. So y is 1/8. Hey, we know what y is, but we still want to know what w is. I have an equation already solved for w. Let's plug into that. W should equal 5 times y. Y is 1/8. So w will equal 5/8. So we just got two things that are really important here. We found y and we found w. Same idea in the other system of equations. Solve for that. Well, I can easily solve for x in this first equation. Just subtract 3z from both sides. So we get x equals 0 minus 3z is negative 3z. Alright, so we use this first equation. We'll now plug in what we know into the second equation here. Negative 3z plus 5z equals 1. Negative 3z is positive 3z. Add those together, we get 8z equals 1. Multiply by 1/8. We get z equals 1/8. Okay, so now we know what z is. Cool. Can still use this second equation here. Now that we know what z is, just do it down here. X equals negative 3 times 1/8 equals negative 3/8. So now we also have, write that below, what X is. And we now have what this inverse matrix should be. W, X, Y, Z should equal, well, what the heck is W? It's 5/8. That's our first entry. What is X? Negative 3/8. What is Y? Well, we found it's 1/8. And what was Z? I think we also found that that was 1/8. I'll write these as more vertical fractions here. And there's our matrix, our inverse matrix, which is pretty awesome. All right, so now we want to verify that it works both ways. The order shouldn't really matter, so let's test it out. Using your answer, I want you to use this inverse matrix, 5/8 times 1/8 times negative 3/8. I don't know why I said times, I mean I'm just listing all these, and we're multiplying that times 1, 3, negative 1, 5. All right, I'm not going to do this for you. Give it a shot. Yeah, it involves a bunch of fractions, but you should ultimately see that you end up getting 1/8. I'll just give you a rundown. You should end up getting 5/8 plus 3/8 here. 1/8 minus 1/8 here. 15/8 minus 15/8 here. And 3/8 plus 5/8 here. Adding those all together, you'll see that you have 1, 1 along the main diagonal and zeros elsewhere. All right, so now it's asking us what is the determinant of that matrix and how is it related to the inverse? So let's think. Take a second. I encourage you to calculate on your own. What's the determinant of that matrix? Well, we know determinants. We multiply the main diagonal, 1 times 5, minus 3 times negative 1 along the anti-diagonal. This gives us 5 plus 3 is 8. Well, we just found that the inverse here is 1, 3, negative 1, 5. Or sorry, that's not the inverse. That was the original. The inverse is 5/8, negative 3/8, 1/8, 1/8. How is that related to this determinant? Take a second. I want you to pause the video and see if you notice anything about this. Well, to me, it seems like in this inverse matrix we found, it's the denominator in every single entry. So it seems like the determinant is the denominator for every entry in the inverse matrix. That can't be a coincidence, right? That's crazy. All right, so now we just want to start to recognize a pattern here. Let's actually list these. So the original matrix that we had was 1, 3, negative 1, 5. The inverse, we found everything was divided by 8, the determinant, and we had negative 3, 1, and 1. So take a second and see if you can recognize any other patterns, anything that's happening to make this matrix turn into its inverse here. All right, for me, I notice now we have a 5 here and a 1 here. Seems like these kind of just switched. That's pretty cool. And I notice, well, this is a 3. It was a 3 there, but hey, now it's negative. So it seems like this changes signs. And similarly, here this is 1. In the original it was negative 1. Well, this also changed signs. And all are divided by the determinant. So we have an awesome pattern that we're starting to notice here. We did all this work up here, but I don't want to do that again. Every time I need to come up with the inverse matrix, I have to sit here and set up 2 systems of equations and calculate that. Shoot me now. Don't want to do it. Let's just instead use these patterns. So for number 3, for each matrix, determine the inverse matrix either by completing the steps outlined in problem 2 or by using any patterns you notice. And you can verify this using Mathway. First though, give it a shot just using the patterns. Alright, for me, first thing I know we're going to need to know the determinant. 2, 2, 0, 5, we're calculating the determinant of this matrix. Well, determinant we know we'll multiply 2 times 5 and then subtract 0 times 2. Do that, we get 10 minus 0, so just 10. The determinant is 10. That means when we're coming up with the inverse of this matrix, 2, 2, 0, 5, we'll use the inverse symbol up here. Every single term should be divided by 10. Because that's the determinant. We know that we will switch these 2 terms, so we'll have 5 and 2. And then we'll take these 2 terms along the anti-diagonal and make those negative. Negative 0, well that's still just 0, and negative 2. And now we technically have an inverse matrix. In math we like to simplify things though. We don't have larger fractions than we need. So 5/10 simplifies to 1/2. 0/10 is 0. Negative 2/10 is negative 1/5. And 2/10 is 1/5. Could have used decimals if you wanted to. So this right here is our inverse matrix. You could test to see if it's true by multiplying it, and you should get the multiplying it by the original, and you should get the identity matrix. Or check it out. If we enter this original matrix, these adds in Mathway are the one problem with it. We multiply the original matrix, which is, well, sorry, we're not multiplying, but if we enter the original matrix, which is 2, 0, 2, 5, you can really just click this arrow and it's going to ask you what you want to do with it. Or you can put the -1 symbol as an exponent almost, -1. And it's going to tell us what the inverse is. 1/2, -1/5, 0, 1/5, which is exactly what we got. Alright, I encourage you to pause the video and give yourself a chance to calculate this one by hand and then check your answer in Mathway. Either way you do it, hopefully you pause the video, you should end up seeing that the inverse is 0, -1/3, -1/3, and 5/9. Alright, last thing we want to do is determine these connections between a matrix, any matrix, we'll call it A, and its inverse matrix, A inverse, and the determinant. Use arrows or generalized formula. Really what I want to do is just come up with this generalized formula here. Right, first thing, what we always want to think about is we need to know the determinant. So determinant of this matrix we've already seen is A times D minus B times C. Again, this means determinant. So we'll always find the determinant first. That's going to be used whenever we calculate the inverse. Well, the inverse of A will be equal to, again, what we do is we switch these two. So it'll be D and A here, and we're going to divide both by the determinant of A. We take the other two terms here, B and D, or B and C, those change signs, so -B, -C, but we also divide these by the determinant. And there is a general formula for this. In general, though, we don't want to write divided by A a bunch of times. We can ultimately factor that scalar value out of this matrix. Realize that we're really just multiplying every entry by the scalar 1 over A, or 1 over the determinant of A. And then it's just D times -B. I keep saying times D, -B, C, A. So this is our general formula. Oops. You can use either of these. It doesn't really matter which one you use. Alright, just to illustrate one more point here. This is an important theorem, actually. What is the inverse of this matrix I'm calling O? Matrix that has all ones. Hence why I called it O. One starts with O. See if you can figure out what the inverse of that is on your own. Alright, for me, first thing we need to know is what's the inverse of O? That's not a 0, that's O. Sorry, not what's the inverse, what's the determinant of O? Well, it'll be 1 times 1 minus 1 times 1, which is obviously going to be 0. Put a slash through it to distinguish between that. So the determinant's 0. Well, if I'm going to use this formula, that means the inverse of O, I'll actually write it both ways, will equal, switch these two, hey, but they're the same thing, so 1 over 0, the determinant, 1 over 0. And then both of the anti-diagonal terms become negative, -1 divided by 0, -1 divided by 0. Or you could have just written this as 1 over 0 times 1, -1, -1, 1. What do we notice here? What goes on with all of these divisions by 0? Well, we can't divide by 0. We know that's impossible. Remember, that gave us asymptotes. It was undefined when we worked with polynomials. So in this case, this is not possible. So what does that mean about the inverse of this matrix? Well, it doesn't exist. There is no inverse for matrix O. So we've just realized that some matrices have inverses, but in some cases they don't. So as a result, what can we conclude? When will they not have an inverse? What did we realize? Well, the determinant is really what caused that. Caused the denominators to be 0. So can the determinant, well, if a matrix has a determinant of 0, will it have an inverse? No. So that's our important theorem here. If the determinant of a matrix is 0, then it doesn't have an inverse. Cool thing though is this works conversely as well, the other way around. Basically, if I flip this statement, sometimes we might want to realize, well, or know that we already have no inverse, therefore we can actually just say what the determinant is. So if a matrix doesn't have an inverse, or it's non-invertible is another way to say that, then the determinant is 0. You'll have a couple one problem on your assignment where it's basically asking you to use this theorem. Notice if a matrix has a determinant of 0 and what that will tell you about whether it has an inverse or not. Hopefully this helps. I think it's really cool, the idea of matrix multiplication, matrices and their determinants and inverses. It's always been a really fun topic for me. Hoping you kind of feel the same and that it's not too difficult. Should you need help, I have tutoring and office hours this week. Only have about 7 more days of the semester and then we're done. Have a good one, guys.